based on what you did in your warm-up, okay, there are a variety of combinations that you could have made. Here are 3 of them. Where we have a circle and a line, we have the parabola and a line, and then the 2 lines, okay? Now, there are some things in these graphs that may not be 100% correct, but let's talk about, first of all, the shading. What are we representing when we shade? Okay, hold on, I had a couple of you. What did you say? Okay, the common solution. So these are the coordinates that work for all of the inequalities that you have up there. Okay? So, like when you graphed the circle and the line, we shaded inside of the circle, we shaded above the line, but the only 2 that overlap, or where they overlap, that's what your actual solution set would be, right? Okay? So what we're going to focus on today is actually graphing these. We'll also work on some application problems with these so that we can move into what we call linear programming tomorrow. Okay? Basically, you have to be able to do a system of inequalities before we can move to tomorrow's lesson. Okay? Now, based on what you did at your group, I am not worried one bit about today's lesson. Because I did not have to give you very many prompts about how to graph these, okay? Now, there are a couple things that I do want to fix about these graphs, okay? And they are minor fixes, and as soon as I put it up on the board, you're going to be like, oh, yeah, I remember that, okay? What I need you to remember is that if you have a strict inequality, we're going to have a dashed line. If you have a like less than or equal to, greater than or equal to, you're going to have a solid line. Okay? Nick did a good job over here with his graph. Okay? Maybe one is solid, one is dotted. Okay? Marissa, you are trying to do you're trying to do the open circle, you have the right idea. But on a graph, we want to make the dashed line. And what's nice, if you accidentally make it solid, right? Just use your eraser and make it dashed. Don't erase the line and redo it. Okay, so what you did with your groups this morning, you individually made an inequality, right? Then you looked at your neighbors, you looked at their graph, you mixed it together with yours, and you shaded the solution set, okay? We're basically going to have to do that all at once, okay? Now, this is something that you did last year. Shake your head if you remember doing this last year, okay? I want to make sure we have a good handle on it in preparation for what we do tomorrow, which you have not seen before. Okay? So, bear with me as we go through a couple examples. Okay? First, I want to talk about the different kinds of solutions that we could get. Okay? No matter what, how many solutions are represented in these pictures? We have an infinite number of points in that solution, right? So we're basically going to get infinite solutions or no solutions, okay? But we represent those infinite solutions by shading where they are, okay? Let's talk about how we know why we shade. You knew that you needed to shade because of the inequality. If we're on a number line, we shade on the number line. If we're on a coordinate plane, we shade the coordinate plane. Okay. All right. So 3 different kinds of solutions. You could get a bounded solution set, which basically means that you have graphs closing in an area of solutions. much like this circle and line that we have graphed right here, the blue plus black. Okay. Now, notice how we have what looks like some corners, okay? These are going to be important. Vertices are the points of intersection that refer to the solution region. So these corner points, or these intersection points that are bounding the area, those are called vertices, and I'm going to ask you to find them. So what I want you to notice in my picture, these blue dots that I highlighted, those are vertices. Yes, this is an intersection point up here, but it's not bounding the area, so it's not a vertex point. Okay. Now, I wish that there was a way for us to find intersections of graphs. Can we do that with algebra? How do we do that, Caleb? What?
Nothing. We avoid it.
We don't avoid it. You've already done it. Okay. Do you remember when we did substitution and elimination? What are we solving for when we do those methods? The intersection point, okay? So now, within these inequality problems, we get to use that in order to find those vertex points, okay? Now, we do have a method called graphing that we could also rely on, and I'll talk about that, but we're going to need to be very, very careful when we do that, okay? All right, an unbounded solution. So here we have some vertex points, but notice how the solution set is just going to grow with the parabola. Okay, it's growing in one direction, which means it's unbounded. Okay, not a big deal today, but it will be a big deal tomorrow. From our warm-up, the people that I had come to the board, we have two solution sets that have unbounded solutions. The red and green together made an unbounded solution towards the right. The two linear ones, I don't know what colors those were, we have an unbounded solution that's going to grow up. And then it is possible for us to not have any points in common. Here you see two parallel lines shaded in opposite directions. Therefore, they're not going to have any points in common. There's no solution. first example is very similar to what you did in your warm-up problem, and then the second problem will be more of an application problem to help us with tomorrow. Okay, so go ahead and write down those two inequalities. X squared plus y squared is less than or equal to 25. And 4x minus 3y is less than 0. Okay, so in blue, let's go ahead and graph that x squared plus y squared is less than or equal to 25. What do we have? We have a circle centered at 0, 0, radius of 5. Now, the bigger question is, do we have a solid or a dashed circle? Okay, we have a solid circle because of the equality that is presented in our inequality. Okay, now, some of you are talking about different ways to determine where to shade your inequality. Since we're going to get into some inequalities that are not always linear, I think the most fail-safe way to determine shading would be to pick a point. Okay, for example, 0, 0, easy point to pick. Plug in, right? As long as 0, 0 is not on your graph, you can plug it in. So 0 squared plus 0 squared, is that less than or equal to 25? Yes, it is. So since 0, 0 satisfies the inequality, we know that we can shade there. So we want to shade inside the circle. Now I'm going to do this with my highlighter. I'm doing this very lightly. So if you're doing your notes right now, I would shade very, very lightly. Because we want to represent the common solutions, okay? This is just giving you kind of basically a note saying, okay, this is shaded on the inside. Okay. Now, let's talk about negative 4x minus 3y is less than 0, okay? It is okay to change it to an equation in order to graph it, okay? 4x minus 3y equals 0, we have a line, right? So I'm going to go ahead and just change it to an equation. And I like putting lines into y-intercept form. Okay. So 4x equals, or slope-intercept form. I do this. Okay, so y equals 4/3 x. Right? All right, so we have a y-intercept of 0, slope of 4, 3. And what kind of line do we have? We have a dotted line because we have strict inequality. Now, when we're trying to decide where to shade, is it a good idea to pick 0, 0? No, 0, 0 is on our line. So let's pick a nice but obvious point that's not on our line. 1, 0 is not on our line. If we plug in 1 for x and 0 for y, does that satisfy our inequality? We would have 4 minus 0 is less than 0. That's not okay. So we need to shade away from that coordinate that we picked since it didn't work. where do they overlap? In this like little semicircle right here, right? So, what I want you to do is dark shade in the solutions that work. Okay, there's the solution set. If you have some really, really light shading and then you really darken in a spot, I'm going to know that that's your solution set. Now, some of you may decide not to shade really lightly and just shade in the solution set. That's fine. But the more of these that we graph, the better it is to maybe make some notes on your paper so that you can see where they overlap. Okay? Now, I would not say that we are done with our problem. Anytime that you graph these, I need you to find the vertices. How many vertices do we have for this shaded area? We have two intersection points. We have this one right here, and we have this one right here. Okay? Now, my graph is not perfect. I tried to graph a circle. Okay? It's circle-ish, but is it a perfect circle? Okay? I know that when you graph these, you may be able to kind of tell where the intersection points are. Okay? If you would like to use your graph to find intersection points, I don't have a problem with that as long as you verify that they're actually intersection points. How do you verify that? Plug them into the equations, okay? So right now, we have x squared plus y squared equals 25, and 4x minus 3y equals 0. Those are the equations that we want the intersection points to. If you think that from your graph you can tell a nice intersection point, plug them into both, and if they satisfy both, that is the intersection point, and you can write that down as one of your vertex points. But if they don't satisfy both, you're going to need to go ahead and use algebra. Okay? So, let's just practice those algebra skills since we have some time. If I wanted to figure out this intersection point, what would be a good strategy to do that? Substitution. So we already wrote up there that y equals, was it 4/3 x? So we can, did you have a question? So you figured it out? Okay, awesome. So we can take this and substitute it into the circle equation. So we get x squared plus 16/9 x squared equals 25. Now we're going to want to add those two together. So what is 1x squared plus 16/9 x squared? Well, that's nice. 25/9 x squared. It's going to be to your benefit to keep things in fractions. Do you guys know how to put numbers from decimals to fractions in your calculator? You guys are looking at me like, what? Okay, now, I think that you should be able to do this without your calculator. However, since your calculator is in your hand, I want to make sure that you know how to do this. Okay? So, Oh no, it's not gonna work. Okay, cross your fingers here, people. Okay, well, that's pretty cool. We'll do this one because it's the same. So let's say you have, what was it, 16/9? And you add 1. Let's just say you do that on your calculator. If you want that to be a fraction, okay, so you already did it, hit math. And the very first thing that pops up is fraction. So hit enter twice, and it'll turn your decimal into a fraction. Okay, that's probably good for you to know. We haven't worked a lot with our calculators this year. Would you agree?
Yeah.
All right, so what's 25 divided by 25/9? 25 divided by 25/9. 9. Don't forget that when you square root both sides, we get plus or minus the square root of 9, which is 3. Okay? We had y equals 4/3 x. So if x is 3, y is 4. If x is -3, y is -4. These would be our vertices, or the intersection points that bound our shaded region. Okay? If from the picture you thought that 3, 4 was a coordinate, plug it in. 3 squared plus 4 squared equals 25. Check. 3 times, was it 3? 3 times 3 plus 4 times 4 minus 4. No, 3 times 4 minus 4 times 3 equals 0. Check. Okay. All right, last question. Okay, so write down some important information. A liquid portion of a diet is to provide 300 calories, 36 units of vitamin A, and 90 units of vitamin C. Okay. Let me see if this is the problem in the book, and then you went to the right book. Okay, just write page 514. It's example 9. That way you don't have to write all of this down. Does that make sense? Okay, a cup of dietary drink X provides 60 calories, 12 units of vitamin A, and 10 units of vitamin C. A cup of dietary drink Y provides 60 calories, 6 units of vitamin A, and 30 units of vitamin C. Set up a system of inequalities that describes how many cups of each drink should be consumed each day to meet or exceed the minimum daily requirements for calories. Okay. Set up a system of inequalities that describes how many cups of each drink. What are the unknowns? How many cups of each drink? So I'm going to call X number of cups of drink X, and Y number of cups or drink Y. So now we need to set up a system of linear inequalities. Okay? Now, This is going to be true for a majority of your application problems. Can we have negative drinks? So x needs to be greater than or equal to 0, and y needs to be greater than or equal to 0. What does that restrict you to? Which part of the graph? Above the x-axis and to the right of the y-axis. So that's basically telling you, hey, focus your energy on quadrant 1. Okay. All right, let's go back and forth here. Now, we are given some information about calories, vitamin A, and vitamin C. So let's group those things together. How many calories are in a cup of drink X? 60. How about drink Y? 60. So we have 60 calories in drink X plus 60 calories in drink Y, and we want to meet or exceed the daily requirements. What are the daily requirements? Meet or exceed. Meet or exceed. What kind of inequality are we going to put there? Greater than or equal to. Okay. Vitamin A, drink X, has 12 units of vitamin A, and drink Y has 6 units of vitamin A. So we're going to make a vitamin A inequality. 12X plus 6Y. We need to meet or exceed the daily requirement, which is, what is our daily requirement? 36. And last but not least, we need some vitamin C, right? So drink X has 10 units of vitamin C, drink Y has 30. And our daily requirement, go back up here to the top, is right here, 90 units. So we want to meet or exceed 90. Okay, so your first step is to actually write that. Right? Now what do we have to do with it? We're going to have to graph them. Now, how many of you want to put those into y slope-intercept form? Don't. It's not worth your time. Okay? It's actually going to be more helpful if we use the intercept method. So let me remind you what that is. If we plug a 0 in for y, we get the x-intercept. If we plug a 0 in for x, we get the y-intercept. And so if you have those two coordinates, we can draw a line through them. Let me show you how easy that is to do. I'm going to do this one in red. Okay? 60x plus 60y equals 300. If I put a 0 in for x and solve for y, what would we get? Five?
4.
We get 5, right? Okay. So 1, 2. So our y-intercept is 5. If I plug a 0 in for y, what would our x-intercept be? 60x equals 300, x equals 5. And which way would we shade? Towards or away from 0, 0? We would shade away, okay? I have kind of a small space. I don't want it to get too cluttered, so I'm not going to do my shading quite yet. Okay? Let's practice again that intercept method. For the second inequality, if I plug a 0 in for x, we have 6y equals 36. What's our y-intercept? 6. Okay? If I plug a 0 in for y, we have 12x equals 36. What is our x-intercept? 3. Okay. And then last but not least, 10x plus 30y equals 90. If we plug 0 in for x, we have 30y equals 90. What's our y-intercept? And if we plug 0 in for y, 10x equals 90. X equals? Here especially is a unit you may want to use a straight edge for. Oops. Now, do you notice how I've been labeling these lines? Okay? When we go to color in the shading, okay, all of these lines we're shading away from. We're going to have to go in here and we're going to have to find the vertex points. Here's what we have. We have a vertex point. I'm going to do this in red. We have a vertex point right here. Okay? 9, 0 is a vertex point. We have a vertex point right here at 0, 6. So we have 9, 0 and 0, 6. Okay? But then we also have vertex points right here, where these two meet, and right here, where these two meet. Now, my graph turned out pretty nice. I think that this coordinate is 1, 4. I really think that that is 1, 4. Now, how do I verify it? That is where the green and red line are intersecting. So I'm going to come here to my green and red equation, and I'm going to make sure they satisfy both. 60 times 1 plus 60 times 4 equals 300. Check. 12 times 1 plus 6 times 4 equals 36. Check. This coordinate right here, it really looks like 3, 2. Well, that's where the blue and red line are intersecting. So I better make sure that 3, 2 actually satisfies that equation. 60 times 3 plus 60 times 2 equals 300. Check. 10 times 3 plus 30 times 2 equals 90. Check. All right. Now, if your graph was not super awesome, not a problem, you're going to have to use some algebra, probably some elimination, to solve for those intersection points. Okay? So how nice is it if your graph is well done? Okay? Okay? But you have to check, right, Eli? If you don't check, then you could get yourself into trouble. Who's to say these are all integer values? Okay? Now, I do have some graph paper in here if you need. Okay? You have to have graph paper for the rest of Chapter 7. Today's stuff and tomorrow and Wednesday's stuff. So if you need some graph paper to do your homework, please come and grab some before you leave. Also, make sure that your partial fraction decomposition quiz is turned into my basket. All right? Yeah. Thank you for your work today.
Thank you.